Bismillahirrahmanirrahim. In our previous lecture we were discussing geometrical meaning of strain tensor components. Today we will discuss stress. We have already discussed that strain and stress are the intrinsic property of an elastic body, that if there is a strain there must be stress, and if there is stress, strain must be produced. When a material is subjected to loads, internal forces are produced within it. That when we apply the force on a material, then internal forces will be produced inside the material. Deformation of this material is a function of the distribution of these forces. The deformation of that material will depend on the forces which are produced within this material. We know that in continuum, stress is associated with internal forces, that an element of the continuum exerts on another element of the continuum across an imaginary surface that separates them. What does this mean? That if you have a continuum and you separate that continuum with the help of an imaginary surface, that you are supposing that we have separated a continuum in two parts with the help of a surface, an imaginary surface. It means that you have two parts. One part is on one side of that imaginary surface, and one part is the other side of that imaginary surface. Then forces will be exerted along that imaginary surface. That one part will exert the force on the other part along that imaginary surface, which is separating the continuum. Stress is basically the system of surface forces producing strain within a continuum. Basically, we have two types of forces. We will study this further: surface force and volume force. Two types of forces. Surface force is a force which have a contact with the body, and a force which do not have a contact with the body is called volume force, like gravitational force. Now, as a result of forces being transmitted within the continuum, the portion of the continuum enclosed by an imaginary surface interacts with the portion of the continuum outside of this surface. That both will exert the force on each other. Interaction. Let us suppose that delta F be the force exerted on the surface element delta S. Now, delta S is the surface area of that imaginary surface which is separating the continuum. Now, we are supposing that delta F is the force which is acting on that surface element with area delta S by the continuum on either side of this surface element and this imaginary surface. That by the continuum, a force delta F is exerted on that imaginary surface with whose surface area is delta S. So what we can write? We can write average force per unit area can be written in this way. Force per unit area, we are denoting this by T. We can take its limit. By taking its limit, we mean that the surface which is separating the continuum in two parts is so small that is negligible. Delta S approaches to zero means that its area is approaching to zero. That is that the imaginary surface which we have supposed that separates the continuum in two parts is approximately zero, means that there is no surface. approximately that limit delta S approaches to 0. There is very small surface, imaginary surface. So this can be written as this. Now what is this n? This n is basically denoting that surface, unit normal of that surface, that imaginary surface, with the help of which you can specify that surface element. This is called the traction vector. Traction vector, this is basically a force. Traction is basically a force. Meaning of traction is the adhesion. And what is delta S? Delta S is basically the surface on which this traction is acting, whose normal is n. Now this is the mathematical expression for traction, and you can have more about this traction by studying the book Waves and Rays in Elastic Continua. From where you can study about the traction. Basically, our objective is to define stress. This stress is related with this traction vector. In an orthonormal frame of reference, let delta Fi be the ith component of the force delta F exerted on the surface element delta Sk perpendicular to the kth axis. What does this mean? That you have a surface element whose normal is in kth direction, and we are supposing that delta Fi is the ith component of this force which is acting on that surface element by the medium. Medium means by the continuum, as we have written here. By the either side of continuum. Now we can define the stress. Tik is defined as the limit of this ratio. Here we have defined Tik equals to delta Fi, force acting on surface element whose surface area is delta Sk, with the limit delta Sk approaches to 0. Tik. This is how we can define a stress. In this manner we can define 9 numbers, because you know that variation of I and K are 1, 2, 3. So you can define T11, T12, T13, T1, T21, T22, T23, T31, T32, T33. We will show that these nine numbers form a second order tensor, and that tensor is known as stress tensor. This is the equation which provides the stress T of TL on a surface of orientation L. This is the equation which provides the stress TL on a surface of orientation L. Now, orientation L means that surface has a normal L in arbitrary direction. We have basically 3 directions, x1, x2 and x3. We have normal in the direction of x1, in the direction of x2 and in the direction of x3. Here we are saying that L is a normal of that surface, but its direction is an arbitrary. That maybe it is not in the direction of x1, x2 and x3. It will be in an arbitrary direction. the 9 quantities, these 9 quantities, which is coming from this equation. These 9 quantities which define the stress state of the distorted medium constitute the second rank tensor. These 9 quantities basically make the second order tensor, and with that second order tensor is called stress tensor. How they can make the second order tensor? Because these Ti small l and these are components of vectors. These are basically, L is, you know that L is the unit normal vector of that surface, and Ti are the components of the traction. These are the components of traction which is acting on that surface. We will show that how these quantities make a second order tensor with the help of this given equation. In this given equation, we have information that these are the components of first order tensor. This is also a component of first order tensor. So this, if the left hand side is a vector, so right hand side must be a vector. So we will start from the definition of a first order tensor and show that these are the components of a second order tensor. There is a derivation behind this equation, but I am not going to do that. I am directly written this equation. No, we will show that these are the components of second order tensor. We know that these are the components of vector. So by definition of vector, we can write this Tik Lk equals to Q T dash J I will be here, and K T dash L dash. Now we are changing K with M. We know that Lk are the components of vector, so we can write L dash M equals to QKM Lk, because these are the components of a vector, so they will satisfy transformation law of a vector, first order tensor. So we will use this here. We have this equation. Now we will take this on left hand side, and we can write this in this way. We know that Lk are the components of arbitrary vector. So this cannot be equal to 0. So this parenthesis will be equal to 0. If this parenthesis is equal to 0, so Tik will be this. Now with the from here we can see that these components are satisfying transformation law of a second order tensor components. It has two free indices and two dummy indices, and with the help of two free indices we can say that these are the components of a second order tensor, and it has 9 number of components. Those are T11, T22, T33. These are called the normal components, and of diagonal components, 6 diagonal components are called shear components. Further, we will see that this tensor is also a symmetric tensor. You will see that how can we prove this tensor a symmetric tensor. We have already seen that our strain tensor is symmetric tensor, and we will see that this tensor is also a symmetric tensor. Now we have total 9 components of this stress. For a vector we have 3 components, and we know that first component is in the direction of x1, second is in the direction of x2, and third is in the direction of x3. So here we will see that 9 components. How can you denote these 9 components, that which component is in which direction? That if you have T13, and then what will you say, that what does this T1313 means? Let's see. This is x1 axis, this is x2 axis, and this is x3 axis. We have made a cube here, so it will have 6 faces. 1 2 3 4 5 6. Now this face which is lying in x2 x3 plane has normal in x1 direction, and this face which is lying in x1 x3 direction has normal x2 direction, and similarly it has normal in x3 direction. Now T33, T32, T331, all the 3 normal components will be in the direction of x1, x2 and x3. They are understood. T33, T11 and T22. Now what is T32? T32 will be in the direction of x2, and T31 will be in the direction of x1. Now if you will talk about this, T22 in the direction of x2 and T23 in the direction of x3, and T21 in the direction of x1. Now T13 in the direction of x3, and T12 in the direction of x2, and T11 in the direction of x1. Now T32, if you have T32, then you can see that it will lie in a plane whose normal is in x3 direction. T32 will lie in a plane whose normal is in x3 direction, and T31 will lie in a plane whose normal is x3 direction. That this first index is telling about the plane. With the help of this first index, you can see that this component will lie in which plane, with the help of first index, and with the help of second index you will tell that it will be in which direction. Suppose you have 2T3, it means that this component will lie in a plane whose normal is in x2 direction, and this is in the direction of x3 axis, normal in x2 direction, so it must be lie in a x1 x3 plane. Now this is x1 x3 plane, so this is x1 x3 plane, and this is T23. That T2 is telling that is a plane whose normal is x2, and this is in the direction of x3. Similarly, if you have T31, it means that this component will lie in a plane whose normal is along x3 direction, and this is the plane. This is the plane x1 x2 whose normal is in x3 direction. This one is, and parallel to in the direction of x1 axis. this is how you can talk about each and every component of this stress. For vector you have three components, and for stress vector, here we have vector, traction vector, force. Stress is also force, second order. Stress is basically internal forces, second order tensor. These internal forces are the second order tensor. And traction is a vector force which has three components. And here stress tensor has 9 components. Now Gauss's theorem. Here we will state the Gauss's theorem, and we will make use of this Gauss's theorem in our next lecture, in which we have to study equilibrium conditions, where we will make use of this Gauss's theorem. Now let us state this Gauss's theorem. We are not going to prove this Gauss's theorem. We have only defined here this Gauss's theorem. So if you have, this is simply conversion of surface and vector, surface and volume integral. Suppose you have surface S encloses a volume V. And Fi is a vector function with continuous partial derivatives. You can write this: F dot n ds surface integral equals to volume integral divergence of F. Sometimes we call this divergence theorem, del dot F dV. That we can move from surface integral to volume integral with the help of this theorem. Further, you can write this is F dot n, so you can write this Fi Ni. This is basically the dot product, scalar product. That if you have two vectors A and B, now what is n? What is n? N is basically the normal of that surface. F and n are the vectors, so you can write the scalar product as Fi and in indices Fi Ni ds. On the right hand side you can write divergence partial Fi, partial I Fi. This can be further written as Fi comma I. These are the notations for the partial derivatives. No, this is for first order tensor. And if you have an nth order tensor, say 100th, 200th, 600 order tensor, then how can you write this theorem for that tensor? Tijkm, Tijk up to m nk. Here Fi Ni nk ds will be equal to volume integral. Here we were taking partial derivative with respect to I in dummy indices. Here the dummy indices is k, so derivative with respect to that index k, partial k Tijk up to m. Further it can be written in this way: Tijk m comma k. They are the partial derivative of this Tijk m. Yeah, this is the divergence theorem, Gauss's theorem for higher order tensor. This is what we have. This is for first order tensor, then this is for higher order tensor. This was today's lecture, and please consult book for more understanding of stress and strain. I have written and I have explained as much as I can, and for you please consult the book, reference book. I have already given you the soft copies of reference books, whether it was Sham series, waves and rays, inelastic continua, wave propagation, elastic solids, And I have also asked you that I have one hard copy of one book. You can also take that book from me. Maybe when we were in our physical mode, maybe you have taken or not, I don't remember, but you have to do that. You have to consult the books for more understanding of stress and strain. Thank you so much. Allah Hafiz.